loved finding it on the mailing list when it was pointed out to me. So this
PDF. Okay.
Yeah. All right. I hope I didn't speak with it on mute now and actually unmuted it, but everyone heard it anyway. So Eric, go ahead. So
all right. I hope I'm also not speaking on mute. Is there any way for me to find out?
Test.
Yeah.
Okay.
Fine.
You're fine.
Okay, I'm fine. All right, thanks. So, welcome everyone. I guess I'm not gonna have to do the present myself part now. I'm Eric, and I'm gonna talk about concurrent class loading. And before we get into it, I have to provide this fun safety harbor statement that basically says you can't trust anything I say. But fortunately, it's all open source. If you have doubts, you can always go and check out the code, see if it's really do what I'm saying. So the agenda for today is the following. First, we're gonna talk a little bit about what is ZGC, what is class unloading, and get an overview over the different phases involved. And then we're gonna deep dive a little bit into code cache unloading and metadata unloading, and eventually get into some kind of evaluation and future plans. Right, so what is ZGC? It is a new concurrent garbage collector introduced in JDK 11, and it's currently an experimental feature, and it works only on x86 64 Linux at the moment, but we're looking into expanding the platform support. And to get a better understanding about ZGC, it's best to look at the goals we have with the project. And as for now, the goals are to scale. And when I talk about scale, I mean we want to be able to run a multi-terabyte heaps and still maintain maximum GC safe or GC pause times of 10 milliseconds. And for this, we are willing to pay a little bit in throughput, but not more than 15% throughput reduction. Another goal that we take very seriously is we want it to be as easy as possible to tune. We don't want 100 JVM flags that nobody knows what they're doing. We want it to work well out of the box as much as possible. And I find that it helps to make everything concurrent to achieve that. Right, so I said it's a concurrent garbage collector. Well, what do I mean by that? G1 is a concurrent garbage collector. Let's look into some details of different operations the garbage collector has to perform. For example, we have to mark all the objects in the heap, traverse the heap and mark all the objects. And we have to perform compaction, we have to defragment memory and clear up large contiguous memory spaces so we can have our bump pointer allocations. We also need to perform reference processing, and we need to have relocation set selection to figure out where is the best bang for the buck to perform compaction. And we need to do a whole bunch of other stuff like string table cleaning and global ref scanning, and most notably class unloading. We need to do class unloading, and we also need to scan thread stacks. So if you look at the notorious normal stop-the-world collectors like serial GC and parallel GC, surprise, surprise, everything is done in a safepoint, and that's the way it works. And if we look at CMS and G1, marking is concurrent. And when I say marking, it's specifically the strong references in the old generation that are traversed concurrently. The rest, such as expanding finalizers and the transitive closure, what's reachable from them, as well as young generation, is done in a save point. And with ZGC, we're checking all the green boxes, except thread stack scanning. Haven't worked that one out yet, but the rest is concurrent. And I've highlighted class unloading here in bold, because that was the last save point operation to bite the dust. It's now done concurrently, and nobody else is doing that. Right, so we released concurrent class unloading for 12. I'm talking in the past tense as if this has already happened. 12 isn't out yet, but it will be in 12. So it's basically checked into 12, and it's on its release train. the traditional phases we have to go through to perform class unloading are the following. Can split it up into first some kind of marking. We have to mark objects, and when we mark the objects, we also mark the metadata reachable from these objects, so that we know what's live. And eventually, we need to perform reference processing. During reference processing, typically you would expand what's reachable from finalizers, which is an additional set of marking that's usually done in a save point. And eventually, we'll get to the unloading part, which is where we walk all of the dead data structures and get rid of all the dead data. So this is both the code cache and the metadata that needs to be purged. With ZGC, we are doing more things concurrently, so it looks quite similar, but not quite. Notably, during marking, when we're marking metadata and objects, we are marking both what's reachable from the strong references and the objects that are reachable through finalizers, so that when our marking terminates, we know the liveness of both final reachable objects and strongly reachable objects, so that the subsequent reference processing is simplified in the sense that it will not change the liveness. It's already been computing during the concurrent marking. And that allows us to continue doing concurrent class unloading as well. And there, again, we will walk the code cache, we'll walk the metadata, and purge out all the stuff that is dead. So the phases for ZGC look something like this. The large downward facing arrows are safepoint operations. We have 3 of them in a cycle. The first one is the mark start safepoint. And there we basically walk the stacks and kick off the concurrent traversal that is running while the Java application is running. And eventually we terminate the marking in mark end. And after that, that's when the liveness information is complete, we know stuff has died. And we start another concurrent phase. And during this concurrent phase, this is where we do concurrent reference processing and concurrent class unloading. Eventually we get to a concurrent relocation phase, but we have a safe one before that where we flip a bit in a global mask, and then we start running and we basically invalidate the whole heap and perform relocation concurrently. So the first step, let's look a little bit deeper in that, marking. We have colored pointers, and that means that the GC faces are tied to a specific color of the pointers. And when we're marking things, we have a peculiar color that we want the pointers to have to mark them as strongly reachable. We also have a particular color for things reachable through finalizers. So the final reachable objects, the pointers have a specific color that is detected in our load barriers. So in our load barriers, we can promote final reachable objects to becoming strongly reachable. And this works in a similar fashion for metadata as well, that the metadata can be reachable through finalizers or strongly, and we need to keep track of which one of them it is so that we can do all magic concurrency stuff. And if we look at what's hiding beneath the objects, the metadata, it looks something like this. So we have a bunch of objects, and you can have a direct link from a Java object to a class loader that will keep it alive. But this is in the case here. We have a class pointer in the header word of each object, and this class we have to mark as well. So when we're traversing through our objects, we're also traversing through the class. And, well, the class has some reference to its class loader data, and the class loader data has a bunch of handles in a handle area that eventually point out the class loader and some mirror classes and stuff like that. So by marking the class, we have to keep all of this stuff alive, basically. But if we haven't found any objects with a class that is that we have marked, and we haven't had objects pointing out class loaders, then we can get rid of everything, and we'll do that. So the next step is reference processing. There's quite a lot to this. I'm going to dumb it down as much as possible for the simplicity of this presentation. So basically, we have the main point is that we have two different types of weak references. The normal weak reference, it gets cleared if the reference is not strongly reachable, but can still be reachable through finalizing and get cleared nevertheless. And the phantom references, on the other hand, they get cleared when the referent is simply not reachable at all, even through finalizers. And why is this important? Well, it's important to us because the VM weak references we have, including the holders to our class loaded data that keeps the classes alive, it has phantom reachability. So we have to be able to lazily compute the reachability of this stuff, which we can and we do. And if the holder of the class loaded data is null through a phantom access, then basically it's dead unless there's some silly reference counter as well, but that's a whole different can of worms. Eventually we get to the unloading part, which is the fun stuff. So after reference processing, there's a whole bunch of different data structures that are now stale and contain dead stuff. There's a subclass hierarchy with the sublinks, sibling, and implementer lists. There's some metadata data objects with profiling data. We have instant class dependency context used for de-optimization. Java lang invoke call sites also have some dependency context that also is used for de-optimization. There's a class loaded data graph. We have a whole bunch of tables. We have so many tables. The protection domain cache table, module table, string table, package table, symbol table. There's a lot of tables. They all have dead stuff now. The list of tables just goes on. And eventually we also have metaspace, which is kind of important that we have a bunch of classes, methods, etc. that all need to get nuked. We have the code cache. In the code cache, we have just-in-time compiled code. This code partially because has dead stuff in it because the object references that have been inlined into the code are pointing to random crap in the heap that is no longer live. And in addition, we have inline caches for optimizing method calls that are also pointing at things that are now dead because the object references died. And the best way of describing this situation is the following. Everything is a huge mess, but we just continue running anyway. Just look at that Juke guy on the motorcycle. He's absolutely crazy. Right, so we want some kind of structure to this madness, and we made a disciplined split between unlinking and purging. So during class unloading, we split everything into unlinking and purging, and it's separated by a thread local handshake operation with all of the threads. And the importance of this is that we want to make sure that we have no racy accesses to these links that we are unlinking when we get to deleting it. So when we purge the data and start deleting stuff, we don't want anyone to be touching this stuff because we will blow up. So that's why we've done it that way. So this goes for metadata, unlink, handshake, purge. And it goes for the code cache as well. A link, handshake, purge. That's the key. Right, so let's talk a little bit more about the code cache unloading. This is the most fun stuff, in my opinion. So I think I need to explain a little bit the two main problems we have here. One is that since we have colored pointers, we have this invariant that all the pointers when we're running have the same color. But when we get to mark start, we start marking. We haven't started marking the object graph yet. We need to assign some kind of color, right, to the immediate values that have been inlined into the native code that we just in time compiled, what color is that going to be? Well, we can't. We have to mark it as marked because that's the phase we're in. But if we do that, we have to also actually mark the objects. And if we're marking the objects, then we have a memory leak because we can't unload stuff. So how are we going to deal with that? Well, somehow we need to defer applying the load barriers to the object references in the native code. Somehow, not gonna spoil yet how that's done. We also have inline caches. They are also very problematic because the inline caches compiled into the native code have cached quick access to wherever they think that a call is going to go. And it might now point at dead machine code. We don't really want to take that call because we'll blow up. So we need some kind of way there of stopping or preventing calls into this machine code with absolutely explosive stuff in it. How are we going to do that? Well, the key to that is end method entry barriers. And these entry barriers basically have a way of arming all the native code in the code cache except what we have on the stack, because that wouldn't make any sense. And trap the next call into that native code. And in that little trap, we get a call, we trampoline into the VM, and in there we can figure out what to do about this possibly stale native code that we've jumped into. And if what we do then is that we traverse the object references in the native code to see, is this thing dead or not? Because that matters to us. If it is dead, then we will de-optimize and basically get back into the trampoline and call a method handle or method miss handler. And in that handler, we will re-resolve the call to something that makes more sense and redo the call into interpreter, whatever we end up in. That makes sense. And for end methods that are good, that they have all the object references are live, it might still be that they have the wrong color, and it might be that they need relocation or remapping because they have some stale pointer value. And what we do then is to remap and paint on the right color that we wanted to have by patching the machine code. And eventually we disarm the barrier by again patching some more machine code. We patch the immediate value in the compare instruction and assign it the global correct value. And that way, when we start running again, everything will make sense. So I have some examples here. I think first example is calling into dead code. What could possibly go wrong? So assume that we are in native method A, and we have this inline cache with a red arrow going down to this potentially explosive native method B. And we call that. Well, then what we're gonna do is we're walking the object references here and find out that, oh, this is really bad. This guy is dead. We should not be calling this code. And then we re-resolve the call and patch into the inline cache in the machine code a jump to, in this example, a compiler to interpreter adapter that will allow us to take the execution over to the interpreter, and it will all make sense, and we might compile new code and stuff like that. Next example is calling into something that isn't dead. So in the similar scenario, we are in native method A, we're calling native method B, and once we enter there, we're calling our little barrier function, and there we walk to oops, and we find that, okay, well, it looks like the object references here are live, but they're a little bit out of sync with reality. So no problem. We patch them up, patch the machine code, and disarm the barrier, and we're good to go. And the subsequent calls into this method through that inline cache will get there without calling that barrier. Right. So from the GC perspective, we had these two distinctive phases that we talked about: unlink, handshake, purge. And yeah, during the unlinking, the concurrently running garbage collector thread, it will clean all the stale inline caches by patching the machine code, and it will resolve some. It has a resolve handler that will patches into the machine code so that it will resolve the call instead of calling this really bad code. And we fix up the object references, also concurrently by the GC thread running. And we also disarm the barriers that the GC thread comes across. And we also unlink dependency contexts. And this is a bit of a lock-free dance going on, where the GC thread is unlinking this while the Java threads are potentially mutating it as well. But it all makes sense, I promise. And a similar story for exception caches, that there's a bit of lock-free code there for unlinking exception caches while we're running.